Hello there. Welcome to the video for Chapter 3, Section 4. This section is going to feel like we're in a whole different math world, talking about permutations and combinations, but hang with me because they actually have real-world applications you may see someday, so it's worth at least seeing how they work. Alright, let's get to it. Welcome to the video for Chapter 3, Section 4. Today we're going to talk about additional topics in probability and counting. Specifically, we're going to learn how to find the number of ways a group of objects can be arranged in order, find the number of ways to choose several objects from a group without regard to order, and how to use the counting principles to find probabilities. Okay, let's get started. To get your mind ready for this group of topics, we're going to start by looking at a situation from two different viewpoints. Picture this scenario. Amy, Bill, and Charlie are performing in an improv competition. Three specific parts are available: the lead, the sidekick, and the silent mime. The judges randomly choose their names from a hat to assign parts. The first name chosen is the lead performer, and so on. List the possible show lineups. What is the difference between the above scenario and just saying that Amy, Bill, and Charlie are all cast members? Well, in the first scenario, order is important. When the judges drew the first name, that determined who was going to be the lead in the performance, and then the second person drawn would be the sidekick, and so on. It mattered who was drawn when. In the second scenario, order doesn't matter. Everyone is just considered part of the cast with equal footing. How do we differentiate situations when order is important versus when it's not? We're going to begin by talking about situations where order is important. Let's start with defining permutations. A permutation is an ordered arrangement of objects. If we have exactly n objects being sorted into n positions, then the number of different permutations of n distinct objects is n factorial. That's what you call that little symbol, the exclamation point, a factorial. So the number of different permutations of n distinct objects is n factorial. That means you multiply n by the integer directly beneath it, then the one under that, then the one under that, until you get to 1. So for example, 6 factorial is 6 times 5 times 4 times 3 times 2 times 1, which equals 720. Same thing with 4 factorial. 4 times 3 times 2 times 1 equals 24. One important note here is that 0 factorial equals 1. So there is no 0 when you're multiplying and dividing factorials. 0 factorial equals 1. Make sure you write that down. Okay, let's go over how to find this on your calculator. I promise it's easy. To quickly perform the factorial function on your calculator, you type the number. For our earlier example, you could use 6, so type 6, then press the math key, then arrow over to the probability, then arrow down to or press the number 4. It has a little exclamation point next to it. Then press enter. It will multiply it out for you. That's simple, right? Okay, let's think about those little Sudoku number puzzles that are so popular. The objective of a 9x9 Sudoku puzzle is to fill the grid so that every row, column, and 3x3 square contains the digits 1 through 9. How many different ways can the first row of a blank 9x9 Sudoku grid be filled in? Well, assuming we're not considering any numbers filled in, that we're just looking at how many numbers we could fill in that row with 9 numbers, we would figure 9 factorial, or 9 times 8 times 7 times 6, and so on. We would come up with 362,880 ways. That's a lot of ways to solve a puzzle. And if you think about it, it makes sense because you would have 9 ways for the first blank, and then you would have already used up one number for when you get to the second blank, so you would only have 8 more numbers to work with. That's how factorial works. Okay, so far we've looked at situations we could use n factorial, and they all had something in common, that there were the same number of objects as there were spots to fill, similar to this picture. What if there are more objects than there are spots to fill in this example? So look at these different situations, A versus B. The first one we would just use factorial. The second one we're going to have to use something a little bit different. That's when we have to consider permutations. A permutation is the number of different permutations of n distinct objects taken r at a time. Here's the formula for a permutation. We read it n permute r. So we have a subindex n, that's the little n at the bottom, that's how you say that, a capital P, and another subindex r. That means taking n objects and permuting them into r spots. That is found by n factorial divided by the difference n minus r and taking factorial of the result of that difference, where r is less than or equal to n. So why do we do this division with n minus r? What we're trying to do here is divide away all the permutations of the leftover objects. Remember, this is the formula to use when there are more objects than spaces to fill. Well, this part of the formula takes care of those extra objects. So we're really doing factorial, but we're taking off all of the extra objects. Okay, let's do an example. That'll help you understand a little bit better. Find the number of ways of forming 4-digit codes in which no digit is repeated. We've had similar situations before when we were taking items out of a group we already knew the number of and not replacing them. Now we're counting how many combinations that are possible, so we're looking for a much bigger number. Okay, back to the problem. So to fill a spot that can have any digit, that means there are 10 possibilities for all the digits 1, 2, 3 through 9 and 0. The fact that they cannot be repeated means that there are 4 unique spots that must be filled a certain way. So we have 10 numbers and 4 spots that need to be filled. This is definitely what the permutation formula is for. So we have n, the number of objects, equals 10, and r, the number of spots, equals 4. Now we just plug into the formula. 10 factorial goes on top, then 10 minus 4 quantity factorial goes in the denominator. If we write these out, you can see that everything after the 6, including the 6, gets factored out with the denominator. All we're left with is 10 times 9 times 8 times 7. That gives us 5,040 ways the 10 digits could be arranged in the 4 spots. Now doing this by hand works fine for a problem like this, but there's a much easier way to do this on the calculator. Let's do that now. To quickly perform the permutation function 10 permute 4, you first type in the number representing n. In this case it was 10. Then press the math key, then arrow over to the probability, then arrow down to or press the number 2. Then type the number representing r, in this case it was 4, then press enter. We get the same answer, 5,040. Make sure you get these down in your notes. Remember how I said to keep a separate place in your notes for calculator notes? This would be a perfect candidate for that section because it makes your life so much easier. If you need to, pause the video and do that now. Okay, here's another example. 43 race cars started the 2007 Daytona 500. How many ways can the cars finish first, second, and third? Pause the video and do this one on your own. Got it? Okay. So you need to select 3 digits from a group of 43. So n is 43 and r is 3. Same instructions on the calculator. We type in the number for n, 43, then press the math key, then arrow over to probability, then arrow down or press the number 2. Then type the number for r, which in this case is 3, then press enter. You should have gotten 74,046 ways. If you had done this by hand, it would be 43 factorial over 43 minus 3 factorial. Everything from 40 on would factor out. Then it would just be 43 times 42 times 41. There is a situation within permutations that is kind of tricky, and that is when we're trying to create a unique order out of objects, but some of them are identical. For instance, if I have 7 blocks, 2 blue triangles, 3 green circles, and 2 red squares, and I order them like this, and then I simply switch 2 objects of the same color and shape, I haven't really created a new arrangement. So I need a way to handle this. It's called distinguishable permutations. Mathematicians have thought of a name for everything, haven't they? Now don't be scared of this formula. It looks like a hairy mess, but it's just saying that if you have multiples of something, you represent one of the types of things, like red squares, once, as they've done here, as n sub 1, and take the factorial of it, and then another type of thing, like green circles, as n sub 2 and take its factorial, and so on. And the n factorial at the top is how many total objects you have. So let's look at this in action. A building contractor is planning to develop a subdivision that consists of 6 one-story houses, 4 two-story houses, and 2 split-level houses. In how many distinguishable ways can the houses be arranged? Okay, so there are 12 houses total, so that is my n. But what are my other numbers? Well, for n sub 1, I'd have 6 for the one-story house, right? And for n sub 2, I would have 4 for the two-story houses, and n sub 3, I would have 2 for the split-level houses. Now, when we put it in the formula, you can see that we're doing similar to the original permutation formula. We're dividing out the extras. In this case, we're dividing out the multiplicities. For every item that has multiples, we're taking its factorial and dividing by it, so it no longer interferes with our count of possible arrangements. So we do the calculation, which, by the way, you can do on your calculator using parentheses, and we get 13,860 distinguishable ways these houses could be arranged. Okay, so far we've been dealing with situations where order was important. Now we're going to look at operation to use when it's not important. It's called combinations. Combinations are a combination of n objects taken r at a time without regard to order. The formula looks like this. You read this: n choose r equals n factorial over r factorial times n minus r factorial. So we've done two things with the denominator here. We did what was done with the permutations, the subtraction, which takes away the extras that don't fit into the number of spots we have to work with. Then we're also doing something else. We're dividing by the number of spots, so it takes away the requirement for the objects to land in specific spots. So we're dividing by two different things here, that difference and also the r factorial. Okay, let's look at an example. A state's Department of Transportation plans to develop a new section of interstate highway and receives 16 bids for the project. The state plans to hire 4 of the bidding companies. How many different combinations of 4 companies can be selected from the 16 bidding companies? Okay, so right away we need to discern that order is not important here. They aren't hiring the companies in any sort of order, so combination is what we want to use here. Also, we want to select 4 companies from a group of 16. So our n is 16 and our r, or number of spots, is 4. So let's plug those into our formula. So 16 factorial, that was our total number, over 4 factorial times 16 minus 4 factorial, which is 12 factorial. If we expand the top one a bit, we can factor out the 12 factorials, and we're left with 16 down to 13 in the numerator and 4 factorial in the denominator. If you've been following along in your notes and doing the calculations, you may remember that 4 factorial is 24, just because we've used it before. Okay, so we need to multiply these top numbers together and divide by 24. That gives us 1,820 different combinations. And you're probably thinking there's a calculator solution for this one too, and you'd be right. Here's how to do that. To quickly perform the combination function for 16 choose 4, do the following. Type the number representing n, in this case 16, then press the math key, then arrow over to probability, then arrow down to or press the 3, then type the number representing r, or 4 in this case, then press enter. Try it yourself with another set of numbers. Okay, so we're going to review what we've learned about counting principles, then we'll do a few problems pulling it all into probability, so you'll see how different concepts work together. So on here, we started a section or two talking about the fundamental counting principle. It says that if one event can occur in m ways and another event can occur in n ways, then the number of ways the two events can occur in sequence is m times n. Next, we had permutations. The number of permutations of n distinct objects was simply the factorial of the number of objects. Remember, that's if you have the same number of objects as the number of spots to fill. Okay, the number of permutations of n distinct objects taken r at a time, remember, where order is important and there are more objects than spots, was n permute r, or this formula, n factorial over n minus r factorial. A different kind of permutation dealt with the case of multiple identical objects, called distinguishable permutations. The way you deal with those is using this formula. N factorial, the total number of objects, divided by the factorial of each item that has multiple. Then finally we had combinations, which are the number of combinations of R objects selected from a group of N objects without regard to order, and it uses this formula. N choose R, or N factorial divided by R factorial times N minus R factorial. Okay, let's pull it all together and do a few problems that use these new principles within probability problems. A student advisory board consists of 17 members. 3 members serve as the board's chair, secretary, and webmaster. Each member is equally likely to serve any of the positions. What is the probability of selecting at random the 3 members that hold each position? So the first question to ask is whether order is important. Even though we see the words equally likely and at random in the question, it actually wants to know if we can pick the 3 members that hold each position, which is order specific. So this is a permutation problem. So there are 17 members, that's our N. There are 3 positions, that's our R. So we can use the formula N factorial divided by N minus R factorial. So 17 factorial divided by 14 factorial. We can factor out 14 and everything after it, so we're left multiplying 17 times 16 times 15. Or, of course, you could have done all this with your calculator. You would have found 4,080 ways the 3 positions can be filled. But wait, remember what they asked is the probability of choosing the correct order. So we're not quite done. What we have done so far is just found the number of ways those positions can be filled. Okay, so what are the possible ways of selecting the exact arrangement of people in the correct positions? Well, there's just one way in order to select them correctly. So we divide 1 by the total number of ways they could be filled. We just found 4,080, and we get the probability of selecting all 3 of them correctly at random to be about 0.0002. Okay, that wasn't so bad, right? Let's do another. You have 11 letters consisting of 1 M, 4 I's, 4 S's, and 2 P's. If the letters are randomly arranged in order, what is the probability that the arrangement spells the word Mississippi? So again, we need to first ask if order is important. Yes, definitely, because we need to get the letters in the order to spell the word. That's the whole point of the question. What else do we notice about this one? Well, there are multiples, so we're going to need to use the formula for distinguishable permutations. So let's figure out what letters we have multiples of. Okay, there's just 1 M, so we don't have to worry about that one. You would just be multiplying by 1. Then there are 4 I's, 4 S's, and 2 P's. So we can use our calculator, or we can do this by hand. Remember to add the M into the total number for the numerator, or you can just count the number of letters in the word. So we have 11 factorial over 4 factorial times 4 factorial times 2 factorial. And we get 34,650 distinguishable permutations of the given letters. Okay, but the question asked, how likely is it that a random arrangement spells the word Mississippi, right? So how many outcomes would give us that event? Just one. There's only one way to spell Mississippi. So we have 1 over, or 1 divided by, our answer, 34,650. So we get about 0.000029. Okay, not much chance of that happening accidentally. Okay, one more. Find the probability of being dealt 5 diamonds from a standard deck of 52 playing cards. Okay, so again, is order important? Well, no, it's not for this one. We don't care what order the diamonds are drawn, just that there are 5 diamonds. So we're dealing with combinations. Okay, so how do we do this one? Well, there are a couple of different things we need to deal with here. We have kind of a problem within a problem because there are different card possibilities within diamonds themselves. Then there's possibilities of getting diamonds out of the total deck. So let's take them one at a time. First, how many different combinations of diamonds could we get? Our N will be 13 because there are 13 diamonds in the deck. And our R will be 5 since that's how many we're selecting. So 13 choose 5, or 13 factorial divided by 5 factorial times 13 minus 5 factorial. We get 1,287 different combinations of diamonds. So that's just one part. Now we have to figure out the number of ways we could get those 5 cards out of the full deck of 52. So we do 52 choose 5, or 52 factorial over 5 factorial times 52 minus 5 factorial. And we get a very big number. We get 2,598,960 different combinations for those cards. Now, in order to get our answer for the probability, we have to combine these. So we take the combination from the first part of diamonds, that's which diamonds we would get, over the likelihood of getting diamonds from the total deck. So 1,287 divided by 2,598,960 gives us about 0.0005 probability. Okay, that last one was a little bit of a doozy, but that just gives you an idea of how these can be combined to probability questions. Okay, you've made it. We are done with the lecture videos for Chapter 3. Make sure you're prepared for the quiz in class. Have all these formulas handy and understand when to use which ones. Also make sure you know where your calculator notes are so you can reach them as well. Good luck, and I'll talk to you in the next video.